July 18, 1946, Kapustin Yar Test Range, Kazakhstan SR. Engineer Mikhail Gurevich knelt in the fine, sun-baked dust of the Central Asian steppe. His callous fingers traced the smooth, curved edge of a metallic disc, 6 meters in diameter, its surface polished to a mirror finish that reflected the cloudless sky and distant mountains. The disc rested on 3 telescoping landing gear, each strut wrapped in oiled canvas to prevent dust from jamming the hydraulic pistons. Behind him, a team of 6 technicians huddled around the craft's small central cockpit, their hands adjusting thin copper wires connected to a panel of dials and gauges. Gurevich flipped open his leather-bound clipboard, comparing the disk's physical dimensions to a set of yellowed, fold-marked blueprints tucked under his arm. The blueprints, stamped with faded swastikas and handwritten German technical notations, had been pried from a rusted metal safe in a Nazi research lab in Breslau 8 months earlier. This was Projekt Lyra, Project Lyre's first operational prototype, the Soviet Union's audacious attempt to turn a failed Nazi flying saucer design into a weapon that could outmaneuver any Allied fighter then in service. He checked his pocket watch, 9:07 a.m. In 13 minutes, test pilot Pyotr Nesterov, who had survived 120 combat missions in IL-2 Sturmovix, would climb into the cramped cockpit, and the team would learn that the saucer could even stay airborne for more than the 10 minutes the Nazi prototype had managed before crashing. It was a moment of quiet tension, the air thick with the smell of jet fuel and the distant hum of a generator powering the test equipment. The origins of Projekt Lyra stretched back to the chaotic final months of World War II, as the Red Army advanced westward through Poland and into Germany. On January 27, 1945, soldiers of the 1st Ukrainian Front's 38th Infantry Division captured the Luftwaffe's Versuchsanstalt für Flugzeugbau VFF, a secret research facility hidden on the outskirts of Breslau, now Wrocław, Poland. The VFF had been disguised as a derelict textile factory, its windows bricked up and its grounds ringed with double rows of barbed wire and guard towers. Inside, amid the charred remains of burned documents, broken aircraft parts, and half-finished jet engines, a squad of Soviet engineers found a metal case buried under a pile of coal in the basement. The case, secured with 3 padlocks, held 47 hand-drawn blueprints for a Fliegen Unter Tas flying saucer. Credited to German engineer Richard Meave, a former Heinkel aerodynamicist who had joined the Luftwaffe's experimental weapons program in 1942. The blueprints detailed a radical disc-shaped craft with a single jet engine mounted vertically at its center, adjustable winglets, small movable surfaces, along its rim for stability, and a cramped one-man cockpit set into the disc's top. Notes scrawled in the margins of Meade's handwriting claimed the saucer could reach 800 kilometers per hour at 12,000 meters, execute 90-degree turns without losing altitude, and outclimb any Allied fighter by 500 meters per minute. The design relied on the Coanda effect, a phenomenon where air flows along a curved surface, to generate lift, eliminating the need for traditional wings. To the untrained eye, it looked like a prop from a science fiction film. To the Soviet engineers who studied it, it looked like a potential game changer. Within 72 hours, the blueprints were flown to Moscow in a locked diplomatic pouch, where they landed on the desk of Lavrentiy Beria, head of the NKVD, Soviet secret police, Stalin's most trusted advisor on weapons development, and overseer of all top-secret military projects. Beria saw more than a curious Nazi experiment. He saw a chance to give the Soviet Union an edge in the looming post-war arms race. The U.S. and Britain were already testing jet fighters like the P-80 Shooting Star and Gloucester Meteor. A functional flying saucer, fast, agile, and visually intimidating, could make the Soviets a dominant air power in Europe, if not the world. On March 12, 1945, Beria signed a top-secret order formally establishing Projekt Lyra, tasking it with building and testing the Nazi-designed saucer within 6 months. He handpicked the leadership team: Mikhail Gurevich, co-designer of the MiG-3 fighter, to lead the engineering effort; Sergei Korolev, a rising star in aerodynamics, who would later design Sputnik and the Soyuz spacecraft, to handle flight stability calculations; and Arkady Shvetsov, a veteran engine specialist who had designed power plants of the IL-4 bomber, to adapt the saucer's jet engine for Soviet production. Gurevich's first challenge was making sense of the Nazi blueprints. They were incomplete. Critical details like the engine's cooling system, cockpit oxygen supply, and fuel line routing were missing. Some dimensions contradicted each other. One page listed the disk diameter as 5.8 meters, another as 6.2 meters, and a third referenced a variable rim width that was never fully explained. To fill these gaps, the team spent 6 weeks cross-referencing the blueprints with captured Nazi technical reports, salvaged from the VFF's fire-damaged archives, and interviewing 3 German engineers who had worked directly on Meade's team. The most valuable witness was Fritz Karl, a 45-year-old aerodynamicist who had been captured during the Breslau raid and brought to Moscow for questioning. Karl revealed that the saucer's design relied on a refined version of the Coanda effect. The disk's convex shape would pull air downward as it moved forward, creating enough lift to keep the craft aloft without wings. He also admitted a fatal flaw. The only Nazi prototype, built in November 1944, had crashed 10 minutes into its first and only test flight. Its Jumo 004B jet engine had overheated due to insufficient cooling, and the saucer had spun out of control when the pilot attempted an emergency landing. Karl also noted that Meade's team had been rushing to meet a December 1944 deadline set by Hitler, cutting corners on stress tests and material quality. Beria ignored the warnings. He viewed the Nazi failure as a minor setback, not a fundamental flaw. In a meeting with Gurevich and Korolev on April 5, 1945, he declared, "The Germans lack discipline. We will build it right." He ordered the team to proceed with construction, using the blueprints as a guide and filling in gaps with Soviet engineering expertise. The project was assigned to Factory Number 156 in Moscow, a sprawling complex in the city's southern district that had previously built IL-2 Sturmovik ground attack planes. Work began on May 5, 1945, with 200 engineers, technicians, and metalworkers pulled from other high-priority projects, including the MiG-15 jet fighter program. The first hurdle was materials. The Nazi blueprint specified duralumin, an aluminum-copper alloy that was lightweight, 40% lighter than steel, but strong enough to withstand the stresses of high-speed flight. The Soviet Union produced duralumin, but in limited quantities, and most of the 1945 production run was earmarked for MiG fighters and Tu bombers. Factory Number 156 had to negotiate with the People's Commissary for Aviation Industry to repurpose 12 tons of duralumin sheets, which were originally intended for IL-2 wing panels. The sheets were cut into curved sections using hydraulic presses that normally shaped armor plating for ground attack planes. Each section was 2 millimeters thick, thinner than the Nazi design specified 3 millimeters, a compromise to save weight and stretch the limited material supply. The sections were then welded together with 1.5 mm thick seams, which were checked for leaks by pumping compressed air into the disc, a pressure 5 atmospheres, equivalent to the pressure at 50 meters underwater, ensured no gaps or weak points. Finally, the entire surface was polished with abrasive pads for 40 hours per disc, reducing aerodynamic drag by 15%, a critical detail for reaching the saucer's target speed of 800 kilometers per hour. The engine presented an even greater challenge. The Nazi blueprints call for a Jumo 004B, an axial flow jet engine that had powered Germany's Me-262, the world's first operational jet fighter. The Soviet Union had captured 12 Jumo 004Bs during the war, mostly from abandoned Luftwaffe bases in Poland and East Prussia, but most were in poor condition, for had cracked turbine blades, damaged by improper storage in freezing temperatures. 3 had clogged fuel injectors from old contaminated fuel, and 1 had a melted combustion chamber, likely from the Nazi prototype crash. Shvetsov's team spent 3 months rebuilding the engines in a climate-controlled workshop at factory number 156. They replaced damaged turbine blades with Soviet-made equivalents forged from nickel-chromium alloy, cleaned the fuel injectors with ultrasonic equipment, and repaired the melted combustion chamber by welding in a new copper lining. Copper's high thermal conductivity helped dissipate heat. They also modified the engine's fuel system, increasing the flow rate by 10% to boost thrust from the Nazi spec 9.8 knots to 10.5 knots, enough, they hoped, to compensate for the saucer's projected weight of 3.5 tons. To prevent the overheating that had doomed the Nazi prototype, they added a second oil cooler mounted on the disk's rim, which drew in cool air as the craft flew and routed it to the engine's oil system. The cockpit, a small pod set into the center of the disk's top, presented its own unique challenges. The Nazi blueprint showed a bare-bones setup: a single canvas seat, a basic speedometer, a rudimentary steering stick, and no safety equipment. Soviet test pilots, however, refused to fly the saucer without additional instruments and protections. Pyotr Nesterov, who had survived being shot down twice in IL-2s, insisted on an altitude gauge to prevent accidental stalls at high altitude, a gyroscope to counteract disorientation during tight turns, a fuel level indicator to avoid running out of fuel mid-flight, and a parachute harness. The Nazi prototype's pilot had died because he had no way to escape. The team added the instruments, but the extra wiring gauges and harness mounting points added 300 kilograms to the saucer's weight. They also reinforced the cockpit with 8mm steel armor plating, protecting the pilot from anti-aircraft fire and debris, but this added another 150 kilograms. By July 1945, Gurevich's team realized the saucer would weigh 3.8 tons, 600 kilograms more than the Nazi design, an increase that would later hurt its speed and maneuverability. By December 1945, the first prototype, dubbed WWII, was ready for ground testing. It was disassembled into 3 main sections: cockpit, engine module, and outer disk, and transported by rail to Kapustin Yar, a remote test range 600 kilometers southeast of Moscow. Kapustin Yar had been established in 1943 as the Soviet Union's primary site for testing rockets and experimental aircraft, its vast, uninhabited steppe offering miles of open space for crashes and mishaps. The first test focused solely on engine performance, with the saucer anchored to a concrete pad by steel cables to prevent accidental liftoff. On December 10, 1945, the Jumo 004B engine was fired for the first time in WWII. The team monitored its temperature, thrust, and fuel consumption using sensors wired to a nearby control trailer. The engine ran for 25 minutes before overheating, double the 10 minutes the Nazi prototype had managed, a small but significant victory. But the test also revealed a new problem. The engine's intense vibration caused the disk's thin duralumin skin to flex, creating tiny gaps between the welded sections. If left unfixed, These gaps could leak fuel or air at high altitude, leading to engine failure or loss of control. The team added 12 steel ribs to the disk's interior, each 10 millimeters thick and spaced evenly around the engine module to reinforce the skin. The ribs added another 150 kilograms to the craft's weight, but they eliminated the flexing, as subsequent tests confirmed. The first attempt to lift off took place on March 2, 1946. Nesterov arrived at the test range at dawn, wearing a fur-lined flight suit to combat the early spring chill. He climbed into the Lyra-1's cockpit through a small hatch on the disk's top, his body squeezed into the tight space. He could barely move his elbows without hitting the instrument panel. The cockpit's polished metal walls reflected sunlight into his eyes, forcing him to wear dark goggles. The engine was fired at 10 a.m., a high-pitched whine that echoed across the silent steppe. Nesterov slowly increased thrust, and the saucer lifted 1 meter off the ground before he cut power and set it back down. "It's like sitting on a spinning top," he told Gurevich afterward, wiping sweat from his brow. "The disc wobbles side to side the second you lift off. You have to fight the stick constantly to keep it straight. And the vibration? It's like sitting on a running washing machine." Over the next 2 months, the team conducted 12 more ground tests, gradually increasing the saucer's lift to 5 meters and its hover time to 3 minutes. Each test revealed new flaws. The landing gear retracted unevenly, causing the disc to tilt to one side. The engine stalled at speeds below 150 kilometers per hour, making takeoff risky. The winglets, meant to stabilize the craft, created unexpected drag that slowed the saucer to a maximum of 350 kilometers per hour, well below the target 800 kilometers per hour. And the fuel tank's placement in the disk's rim caused fuel to slosh during turns, disrupting engine performance. Gurevich's team spent 6 weeks revising the design to address these issues. They replaced the telescoping landing gear with fixed struts, simplifying the mechanism and cutting 200 kilograms of weight, though this meant the saucer sat lower to the ground, increasing the risk of damage during hard landings. They adjusted the winglet's angle from 15 degrees to 10 degrees, reducing drag while still providing enough stability to minimize wobble. They also added a small vertical tail fin, a deliberate deviation from a Nazi blueprints, mounted on the disk's rear to improve directional control. Korolev initially argued that the fin would disrupt the Coanda effect by altering airflow over the disk's surface, but wind tunnel tests at Moscow State University proved it helped. The saucer's side-to-side wobble decreased by 40%, and its ability to maintain a straight course improved dramatically. To fix the fuel sloshing issue, they added internal baffles to the fuel tank, thin metal dividers that prevented fuel from shifting too quickly during turns. By June 1946, the Lyra-1 was ready for its first short control flight. On June 28, 1946, Nesterov piloted the Lyra-1 for a 5-minute test flight. He lifted off at 10:30 a.m., climbing slowly to 100 meters to avoid stalling. He accelerated to 200 kilometers per hour, flying in a straight line for 2 kilometers across the steppe, then made a gentle left turn, banking no more than 10 degrees to avoid losing control, and landed safely. The team cheered as he climbed out of the cockpit, his face flushed with excitement. "It flies," he said simply. The flight was a modest success, the first time a Soviet-built flying saucer had completed a controlled takeoff, flight, and landing, but it also highlighted how far the project still had to go. The saucer was slower than planned, less maneuverable than hoped, and still prone to vibration. Beria, who had traveled Kapustin Yar to witness the test, was pleased enough to authorize construction of a second prototype, the Lyra-2, designed to be combat ready. The Lyra 2 would incorporate all the fixes from the Lyra, 1 test, plus a more powerful engine and a small bomb rack. Work began immediately at factory number 156. The team replaced the rebuilt Jumo 004B with a Soviet-built RD-10, a licensed copy of the Jumo 004B, but with an improved fuel injection system that reduced stalling and increased thrust to 11 knots. They increased the fuel tank capacity from 300 liters to 500 liters, extending the saucer's range to 500 kilometers, enough to reach Berlin from Warsaw and return. They also added a small, retractable bomb rack under the disc's belly, capable of carrying a single FAB, 100 high-explosive bomb, 100 kilograms of TNT wrapped in a steel casing, enough to destroy a tank column or a small bunker. The Lyra 2 was completed on July 15, 1946, and transported to Kapustin Yar by rail, its disc wrapped in canvas to hide it from curious onlookers. July 18, 1946, dawned clear and hot. Temperatures reached 32 degrees Celsius by mid-morning. Perfect weather for flight tests, as the dry air reduced engine overheating risks. The team arrived at the range at 6 a.m., unloading tools and test equipment from a truck. They spent 3 hours checking the Lyra 2's engine, adjusting the winglets, and calibrating the instrument panel. Nesterov arrived at 8 a.m., accompanied by a medic who checked his blood pressure and heart rate, standard procedure for experimental flights. He put on his flight suit, strapped on a parachute, and climbed into the cockpit at 9:15 a.m. The engine was fired at 9:20 a.m., its whine louder and steadier than the Lyra ones had been. The Lyra 2 lifted off smoothly, climbing to 500 meters, higher than the Lyra 1's maximum altitude, and accelerating to 400 kilometers per hour. Nesterov flew in a wide circle over the steppe, then attempted a gentle left turn. The disc responded sluggishly, banking 20 degrees more than he intended, but he corrected with the stick and maintained control. Encouraged, he accelerated to 500 kilometers per hour and tried a tighter turn, 30 degrees, but the disc began to spin a flat spin, where the craft rotated around its vertical axis without losing altitude. Nesterov cut power immediately and the spin slowed, but the engine sputtered as fuel sloshed in the tank. The baffles had reduced, but not eliminated the problem. He glided back to the test range, landing hard. The nose gear collapsed under the impact, scraping the disc's front edge along the ground and damaging the engine's oil cooler. The crash revealed a fundamental, unfixable flaw in the Nazi design. The disc shape made it inherently unstable at high speeds. Airflow over the curved surface created lift pockets, areas of low pressure that pulled the disc off course, especially during turns. The winglets and tail fin helped mitigate the issue at low speeds, but at speeds above 450 km per hour, they were overwhelmed. Shvetsov's team also discovered that the RD-10 engine, despite its improvements, was still underpowered. The Lyra 2's weight, now 4 tons with a bomb rack and additional armor, meant the engine could only push it to 550 kilometers per hour, 250 kilometers per hour less than the Nazi blueprints had claimed. Even if the stability issue could be solved, the saucer would still be slower than the American P-80 Shooting Star, which reached 932 kilometers per hour, and the British Gloucester Meteor, 668 kilometers per hour, making it obsolete as a fighter. Beria ordered the team to find a solution, but by late 1946, the Soviet Union's military priorities had shifted dramatically. Stalin, alarmed by reports of American jet fighter development, had ordered a crash program to mass-produce the MiG-15, a proven design that could be built quickly and cheaply. Projekt Lyra With its repeated delays, uncertain performance, and high cost, each prototype cost the equivalent of 10 MiG-15s, was deemed a luxury the Soviet Union could not afford. The project's budget was cut by 50% in August 1946, and half the team, including Korolev, who was reassigned to rocket research, was pulled to work on the MiG program. Gurevich fought to keep Project Lyra alive, proposing a third prototype with 2 engines instead of 1, arguing that dual RD-10s would provide enough thrust to stabilize the disc and reach 700 km per hour. But Beria refused. In a meeting on October 1st, 1946, he told Gurevich, "We need fighters that can fly today, not experiments that might fly tomorrow." The final test of the Lyra program took place on October 5th, 1946. Gurevich's remaining team had modified the Lyra II in secret, adding a small 1.5 can auxiliary jet engine to the disc's rear to boost thrust. Nesterov volunteered to fly it. Despite the risks, he lifted off at 11 a.m., climbing to 800 meters and accelerating to 600 kilometers per hour, the fastest a saucer had ever gone. He attempted a series of gentle turns, and the disc remained stable, but when he tried a sharp left turn at 500 kilometers per hour, the disc spun out of control again. Nesterov cut the auxiliary engine and managed to regain control, but the main RD-10 engine was damaged beyond repair by the stress of the spin. He landed safely, but the Lyra II was no longer flyable. Gurevich wrote in his final report, dated October 10, 1946, "The design is fundamentally flawed. The disc shape cannot be made stable at combat speeds, even with dual engines. The project requires further research that exceeds our current technical capabilities and budget. I recommend terminating Project Lyra." On November 12, 1946, Beria signed an order formally canceling Project Lyra. The Lyra I and the damaged Lyra II were disassembled at Kapustin Yar, their derailment sheets sent back to factory number 156 to be recycled into MiG-15 components. The Nazi blueprints were filed away in the NKVD's Moscow archives, marked top secret, not for further development, and sealed in a lead-lined box. Gurevich was reassigned to lead the MiG-17 development team, where he would go on to design one of the most successful fighter jets of the Cold War. Shvetsov returned to designing engines for bombers, and Korolev threw himself into rocket research, laying the groundwork for the Soviet space program. The flying saucer, once hailed as the future of Soviet air power, was consigned to obscurity. The captured Nazi blueprints that had inspired Project Lyra held a final secret. Richard Meade, the German engineer who designed the original flying saucer, had fled Argentina in May 1945, taking copies of complete blueprints with him, including critical details he had deliberately omitted from the versions left in Breslau. These missing details included a stabilizer ring, a circular metal band around the disc rim that adjusted airflow to reduce lift pockets, and a more efficient engine cooling system that used liquid nitrogen instead of air. Meade later claimed in interviews that the Nazi prototype had been intended to carry a single bomb, but the Luftwaffe had canceled the project in 1944 due to fuel shortages and the engine overheating issue. He tried to sell his complete blueprints to the Argentine government in 1947, but the deal fell through when Argentina could not afford the development costs. Meade died in 1958 in Buenos Aires, his flying saucer design unbuilt and largely forgotten. In the decades after the war, Project Lyra remained a closely guarded Soviet secret. Leaders feared that revealing they had copied a Nazi weapon, even a failed one, would damage their image as a self-sufficient, technologically advanced nation that had defeated fascism through its own strength. It was not until 1991, after the collapse of the Soviet Union, that the project's files were declassified. Historians found them in the archives of the Russian Ministry of Defense, tucked between reports on V-2 rocket tests and early jet fighter development. The files included Gurevich's test reports, Korolev's aerodynamic calculations, handwritten notes from Beria, and even a handful of black and white photographs of the Lyra 1 and Lyra 2 on the Kapustin Yar tarmac. Today, only fragments of the Lyra prototypes survive. A 30-centimeter piece of the Lyra 2's duralumin skin, scored and dented from its final crash landing, is on display at the Central Museum of the Russian Air Force in Menino, outside Moscow. The skin's polished surface still reflects light, and a small, understated plaque explains its origins. Fragment of Project Lyra Flying Saucer, 1946. Built from captured Nazi designs, this prototype tested the limits of Soviet aeronautical engineering during the early Cold War. The Nazi blueprints, their edges frayed from decades of storage and handling, are kept in a climate-controlled vault at the Russian State Military Archive in Moscow. Researchers can view them by special permission, but photography is strictly forbidden to prevent reproduction. The Lyra project's technical legacy is minimal, but its lessons are lasting. It taught the Soviet Union's weapons designers to approach capture technology with skepticism, to verify every detail, cross-reference every claim, and never take a foreign design at face value. The team's reliance on incomplete, flawed Nazi blueprints led to avoidable mistakes, from the underpowered engine to the unstable flight characteristics. After Project Lyra, the Soviet military shifted its focus to original research and development, investing heavily in aerodynamics, engine design, and control systems, work that would lead to the MiG-21, one of the most widely used fighters in history, Sputnik, the first artificial satellite, and the Soyuz spacecraft, still in use today. The saucer also highlighted the inherent limitations of exotic aircraft shapes. While disc-shaped craft offer theoretical advantages in lift and speed, they require advanced control systems, like fly-by-wire technology, to remain stable at high speeds. The Soviet Union lacked this technology in 1946. It would take until the 1980s, with the development of computerized flight controls, for flying saucers to become even remotely practical, and even then, they remained experimental, with no nation ever deploying one operationally. For Mikhail Gurevich, Project Lyra was a brief, frustrating detour in a career defined by success. He rarely mentioned the project in later interviews, but when pressed in a 1972 conversation with a Soviet aviation historian, he said, "Lyra taught us more than any successful test. It taught us to question everything, every assumption, every blueprint, every claim. You don't build a weapon by copying. You build it by understanding. And sometimes you learn the most when things fail." The story of the Soviet Union's World War II flying saucer is a cautionary tale about ambition, haste, and the dangers of technological shortcuts. The Soviets wanted to turn a Nazi relic into a symbol of post-war power, but they ignored the gaps in design, the limitations of their own industrial capacity, and the simple fact that the Nazi prototype had already failed. The Lyra was a machine built on hope. Hope that a captured blueprint could shortcut years of research. Hope that a strange, disc-shaped craft could outmatch proven fighters. Hope that the scraps of World War II technology could shape the future. As visitors to the Central Museum of the Russian Air Force stand before the Lyra's duralumin fragment, they often wonder what might have been if the Nazi blueprints had been complete, if the Soviet Union had had more powerful engines, if the disc had been more stable. Would the flying saucer have changed the Cold War? The answer is almost certainly no. The Lyra lacked the range, speed, and reliability of traditional fighters. It would have been expensive to mass-produce, difficult to maintain, and obsolete within a decade as jet technology advanced. Even if it had worked, it would have been a novelty, not a game-changer. The Soviet Union's World War II flying saucer was never more than a test-range prototype, a machine built from borrowed dreams and incomplete plans. It failed to fly well, failed to impress military leaders, and failed to change the course of history. But in its failure, it taught a valuable lesson. True technological advantage comes not from copying others, but from mastering the science behind the designs and knowing when to abandon a bad idea. Today, Kapustin Yar remains a top-secret test range, though it now focuses on modern missiles and drones rather than flying saucers. The steppe where the Lyra once wobbled into sky is quiet, the dust still blowing across the empty land, the only sound the wind and the distant roar of jet engines. The flying saucer is gone, but its story remains, a footnote in WWII's race for strange weapons, a reminder how even the boldest technological gambles can crash back to Earth.